Hello everybody, my name is Rafael Torres-Orozco. I am a PhD in Earth Sciences and I am specialized in the line of research of physical and experimental volcanology. And today I'm going to show you some of my most recent work, which is on geological and experimental research or studies on volcanic conduit processes and eruption styles using synchrotron and lab-based X-rays microCT. So first, the contents of this presentation are going to be how are volcanic eruptions produced. First of all, magmagenesis, volcanic conduit processes, which are my main area of interest, and eruption styles. Second, methods to study these eruptions, which are microCT methods, lab-based and synchrotron-based X-rays microCT. Two examples from Mount Taranaki, New Zealand, and an experimental example, which is in situ real-time magma degassing at magmatic pressure and temperature, and some few conclusions. So, how is magma generated and how are volcanic eruptions produced? Magma is a process that happens at depths of the mantle or the deep crust. So the magmagenesis depends first of all on the tectonic setting, whereas whether it is a junction in between two tectonic plates where one goes below another, which is called subduction zone, or whether it is in the middle of a tectonic plate, like in Hawaii, for example. So depending on the tectonic setting, we are going to have different processes forming different types of magmas. And magmas form mainly through partial melting of either the mantle or the lower crust. Normally, there are also some processes which is a process which is called metasomatism, in which partial melting of magma involves also transport of fluids from some other areas. And these fluids could be water, could be a different set of volatiles which go together with the silicate melts, and they are transported up to the end on the surface, producing volcanic eruptions. So something important is that when magma is produced and it travels up to crustal levels, it can actually recharge magma reservoirs where there was already magma sitting. When this recharge happens, there is an input of volatiles and heat, which is also producing different processes in this magma on storage, which are fractional crystallization and assimilation of the hosting rocks, and also magma mixing. But the important thing is that all of these processes transform the chemistry of the magma, and so the resulting type of volcanic eruption that might or might not happen. So volcanic conduit processes are going to be those processes happening in the last stage of magma transport before an actual eruption is produced. So these processes happen during disequilibrium, that is, during magma ascent to the surface before it fragments and explodes forming an eruption. So depending also on these processes, how they happen, to what extent they influence magma rheology, we will have different results. And these results being different types of eruptions. So from these types of eruptions or eruption styles are basically going to depend on two different attributes, which are the ascent rate of magma and the outgassing efficiency. So the fastest the magma is ascending, we will have more explosive eruption, like that of Mount St. Helens in 1980 by a decompression wave. But also, the more outgas the magma, the less explosive it will be. So we will only have eruptions comprising lava flows, for example. So in this whole classification, my main interest as a researcher, as a volcanologist, are eruptions produced by decompression, down decompression mainly, or conduit decompression also, gelding into andesitic plinian eruptions like these ones from Kelut and Merapi in Indonesia, Colima in Mexico, Taranaki in New Zealand. I'm also interested in some of these eruptions produced basically by decompression waves, triggering huge andesitic to dacitic plinian eruptions like these Pumice deposit from Popocatépetl volcano in Mexico. So how do we determine, or how do we study these processes inside the conduit using microCT methods? Well, first, what are the advantages of microCT methods? Number one, they are non-destructive. So we can basically just set up the sample inside the instrument, scan the sample, get some nice 3D renderings, and all of that without destroying the sample. We can still use the same sample for other types of analysis. And also that the data that we are going to acquire is, we can do quantitative analysis with it. This is quantitative analysis of materials. The 3D reconstructions that we can produce are virtually, they come from virtually unlimited planes, and that's a huge difference compared to two-dimensional types of analysis. Another advantage that we can do with microCT method is that we can perform in situ and real-time or 4D observations of experimental processes like magma flow, for example, or magma evolution. It's easy to fast to prepare samples. We don't need to do much. We just basically need to cut the sample to a certain size, depending on the resolution that we are targeting. And then we set up the sample inside the instrument. Doesn't matter if it's a lab-based or synchrotron-based instrument, it's just a very simple setup. We scan and we acquire a set of images. Could be hundreds to thousands of images, and these are 360 degrees images of rotation. What we are looking to these, we are looking at this grayscale, which corresponds to different attenuation coefficients. That is the X-rays absorption of each different component that comprises our sample, and that absorption of X-rays depends on the atomic number of each component. So we have very bright materials, which are oxide crystals, and we have not so bright materials, which are basically correspond to glass, to the glass ground mass. At the end, we can reconstruct this data, produce these renderings, 3D renderings, and we can also segment the different phases. In this case, we have crystals, bubbles in light gray, and ground mass in yellow. And we can still also separate every phase and calculate different shapes. For example, these are pores or bubbles with different colors, which correspond to different bubble sizes. And a lab microCT looks something like this. It's an instrument which basically uses the space of a room. And what does a microCT, what does it consist of? We have an electron source, which could be a cathode or a filament, which is shooting electrons towards a place. In this case, it's a crystal, towards another part of the instrument in which electrons will crash, and due to this crash at a very fast speed, they are going to release energy, and this energy is within the wavelength of X-rays. Then we capture those X-rays and make them pass through a filter in order to scan our sample, and from these, then we get the different attenuation coefficients that are going to be captured by our detector and then recorded with a camera. And synchrotron is basically the same, but at a huge and very larger size. This is the diamond light source in the UK, the Australian synchrotron, and the European synchrotron in France, 3 of them in which I have experience working in. But how does a synchrotron look inside? Well, a synchrotron is basically this kind of spaceship look ring from inside. And to understand, this is nearly the same like with the lab microCT. We have an electron source, an electron gun, shooting electrons into a ring, a storage ring. And in these storage ring, electrons are moving in a circular way. Why are they moving in this circular way? Because there are some magnets producing magnetic fields in which electrons are hitting, and then electrons are crashing, I mean. And when they crash, well, the magnetic fields, move electrons in this circular way. And once the electrons crash, they release energy. And again, the fastest the electrons are crashing, this energy will be the highest. And the higher the energy, that means that it can range within the wavelengths of X-rays. And once we have these X-rays produced, we can direct these X-rays through a beam line into an experimental hotch. Now, what is an experimental hotch? How does it look like? Let's look at I-12 hotch in diamond light source in the UK, where I've been working most of my times for the last years. So this looks like very complicated, like a lot of information in one picture with lots of cables. However, this is very simple. We have an X-ray source of light with a monochromator, which is transforming the source of light into monochromatic light, which is finally passing through our sample. Our sample is sitting somewhere here inside our pressure temperature rig. This pressure temperature rig, which is called P2R, was designed in my group in the UK within University College London and Manchester. And once the X-rays pass through our sample, we can capture the different attenuation coefficients resulting from the sample with our detector and recording them with our camera. The rig is sitting over a rotation platform. However, in this setup, we don't have the platform rotating, because what is actually rotating is the rig. And it more or less looks like this. Now we have the high pressure temperature rig working. It looks red inside because the temperature is about 1000 degrees Celsius. So, sorry. This is another setup with only a furnace without a high pressure rig, in which we can perform temperature experiments only to see, in this case, how magma is changing, well, with temperature. The advantage of this furnace is that we can very fast heat or cool the sample. So again, some advantages of this setup is that we can capture in situ real-time experiments of dynamic processes of magma flow, or how magma is evolving through time. Setting up these instruments takes about 1 hour, and then performing the experiment is just about 30 to 60 minutes. So we can do plenty of experiments, at least 12 different experiments in a day of work inside the hotch. Okay, now some practical examples of using microCT techniques. This is we're moving to Mount Taranaki in New Zealand. So Mount Taranaki is a volcano that has erupted many large eruptions during the last 5,000 years. So this is just one of them. And this one, which is 3,300 years before present, is special because it comprises a set of different layers of different types of rocks, which correspond to different eruption processes. And this also has a chemical composition characteristic, but those eruption processes correspond to these maps. We can see different things happening during the eruption, from a column which is spreading ash all over the Taranaki Peninsula in the North Island of New Zealand, to different pyroclastic density currents which are moving due to gravity over the volcano flanks. And it looks like this. A volcano which is just sitting there, it starts erupting due to dome collapse, which is producing these pyroclastic density currents moving due to gravity. Then we have a Plinian column being erupted We also have a lateral pyroclastic density current moving because of internal pressure more than gravity. And we finally have the column collapsing and the eruption ending. This is a huge eruption, which we can classify in the volcanic explosivity index of 4, which is similar to other types of plinian eruptions in the world. So once we get all of that sorted from field work, we can in fact understand what are the components of every layer produced by this eruption. From studying all the components of every layer, we ended up with at least 5 different types of vesicular fragments. And these vesicular fragments comprise different textures, from one which is full of different bubbles, which is a foamy texture. Then we have very thousands also of bubbles, but smaller in size. Then we have bubbles which are deformed by shear forces, bubbles with very thick walls, and bubbles with the thickest walls, and this texture also has the highest crystallinities. So we have a range of different textures produced during a single eruption and produced in different volume percentages. So this data, what it tells us, the last slides I was only showing 2D images, but once we get the 3D data, we can actually really quantify the input of every different type of rock texture into affecting the rheology of magma, and so on, and so the type of eruption which is being produced. The type of data that we acquire is the porosity, crystallinity, geometry of bubbles, geometry of crystals, bubble and crystal number densities. How all of these changes the magma, the rheology of magma during the eruption time. So this type of work is also time constrained due to a stratigraphic time constraint. And so we can understand processes inside the volcanic conduit driving this eruption with time. We end up with these very nice 3D volume renderings in which we can separate whole rock into crystals, into matrix, and also into pores. And in this case, pores are classified with using colors. They are classified by volume. The type of data, the evidence that we acquire from this 3D quantitative analysis is how disequilibrium processes actually affect magma rheology in multiple ways prior and during the eruption, and this in turn is used to understand how the eruption styles change with eruption time. The eruption styles transitions, and we saw that we had down collapses changing into blast density currents, changing into plinian column, and this is all telling us a history of magma rheology inside the volcanic conduit during a volcanic eruption. So let's move to the next one. So now another example is what we can do with experiments. The previous example was what we can do with geology and microCT, synchrotron microCT. Now, what we can do with experimental volcanology and synchrotron experiments. So this is an experiment of in situ magma degassing at pressure and temperature. This is our starting material, which is an obsidian, more or less homogeneous, of rhyolitic composition. We picked up this small piece of the obsidian to start our experiments, but before we pick it up, or before we core this small sample, we need to make sure that the obsidian is actually homogeneous. Homogeneous means that it has no banding of crystals or vesicles that could make it heterogeneous in different areas. That the porosity, the crystallinity are nearly nothing. The water content is also very low. Initial bubble number density is also low. And these are only the metrics of the sample from this core and the subsample that we use for quantification. Now, the experiments of thermal vesiculation by changing temperature but at atmospheric pressure were fast degassing, in which we just increase the temperature very fast and then we cool. slow degassing, in which we increase the temperature in very slow steps, increasing also, of course, the dwell time of the experiment. And then we have a slow increasing of temperature and then very fast heating until we finish the experiment by cooling. And in these videos, we can see the difference from fast vesiculation to very slow. We immediately see bubbles forming in both, even though the speed is different. However, in the slow to fast, we see nearly nothing for a while. For almost half of the experiment, we see nothing. And then suddenly, from nothing, we move very fast to thousands of bubbles. To thousands of bubbles here, from nothing to thousands. And our final porosity will be much higher, 70 to 73 volume percent final porosity compared to the 45 to 55 of the other two experiments. So this was a very nice discovery. And in all of them, we saw nucleation growth and coalescence of bubbles. So that's also interesting. We have another set of experiments in which we produce vesiculation, but not during temperature, but controlled by pressure, by pressurizing and decompressing. So here we were first pressurizing to make the sample very homogeneous, and then we start decompressing using this piston, which is the black area inside the sample holder or sample container. So this is magma, and we were just vesiculating, producing the small bubbles, and then we move the piston down, back, in order to make them dissolve again into magma. We can also look at deformation structures thanks to compression, thanks to pressure. But this is one of the nicest experiments. We had the sample, we started decompressing, forming bubbles. The bubbles can even expand to very big sizes. We then try to redissolve gas into solution to a point in which the pressure is so high that the sample container is going to break. And when breaking in this side, we are going to produce rapid decompression, vesiculation, and thousands of bubbles, which we can also see here. Another thing that we can do is to, well, because this is a 4D experiment, and that means changing magma with time and with temperature in the first case and pressure the second case, we can correlate these different volumes during the experiment and observe how porosity, bubble number densities are changing, but mainly how the expansion and growth of the whole sample is producing magma ascent. We have bubbles nucleating, but as the foam, magma foam, moves upwards inside the sample container, that means we have magma ascending, and that we can also calculate, magma ascent. When we move to the particle level, to the particle scale, we can also track in bubbles individually to see how they change, in this case, in size, with time, with temperature, or with pressure, and measure individual geometry, individual evolution of each bubble, or bubbles geometry, nucleation and growth, movement of bubbles, bubble distribution, and coalescence, forming these very large blue bubbles. And what we saw, for example, in the slow to fast degassing experiment, is that when we reach certain threshold during experiment at 67 minutes, you can see how bubbles become very homogeneous in shape and in size. And this homogeneity matches with numbers that are that correspond with natural samples produced by Plinian eruptions, like the largest eruptions. So we basically produce a Plinian eruption inside the lab. And we were able to record it using synchrotron X-rays. So finally, doing these experiments, we get plenty more of new insights into bubble nucleation and growth. In radioactive magmas, in this case, there are also in basaltic magmas or all sorts of compositions, percolation thresholds, and how these associate with different eruption styles. And of course, because this is a quantitative study, we can study nucleation and growth rates and bubble distributions with time, how they evolve with eruption time. And in this work, we have several papers being in preparation, like this one, which is the kinetics of decompression-induced vesiculation, how these will influence also the types of eruptions, explosive, effusive, and understanding the dynamics of bubble nucleation controlled by decompression, or sudden, fast, and slow, well, is very relevant for volcanic eruptions. As I said, we can also look at the movement and growth and redistribution of individual bubbles. In this case, here we have a single bubble changing with experimental time, dwell time, but we also can track the movement of that bubble inside the whole flow, and this bubble is moving a lot. And finally, we also see how bubbles nucleate, coalesce with time, I'm sorry. In this case was very interesting, because normally what we would expect is to see two bubbles merging together and forming a huge one. But in this case, even when they coalesce, we can see like this amorphous thing, bulging bubble with appendixes hanging from sides. So that was something interesting to see, and I think this is going to be first described. So conclusions: using the microCT techniques, we can either we use a geological approach or an experimental approach. Using both, we can get quite a lot of insights into what was happening inside the conduit, what was happening with disequilibrium processes driving volcanic eruptions, so that we can understand how different eruptions of different intensity and of different style can happen, and of course interpret the conditions and the processes driving these eruptions inside the conduit. Thank you very much, and thank you for watching.